Hi, welcome back to LeetCode. In this one, discuss LeetCode problem 3419. Minimize the maximum edge weight of graph. So you are given two integers n and threshold, as well as directed weighted graph of n nodes numbered from 0 to n minus 1. The graph is represented by 2D integer array edges, where edges I represent ai, bi, weight wi. So ai this means what? There is an edge from ai to bi. This is a directed graph. That's why the edge direction is from ai to bi with the edge weight as wi. So you have to remove some edges from this graph, possibly none, so that it satisfies the following condition. What are those conditions? Condition is that node 0 must be reachable from all other nodes, and the maximum edge weight in the resulting graph is minimized. So we have to minimize the maximum weight in the resultant graph. And first condition is that also that from all other nodes there should be at least one path to reach node 0, right? Third condition is that each node has at most threshold outgoing edges. So in any node we will have maximum threshold number of outgoing edges. So return the minimum possible value of maximum edge weight after removing the necessary edges. If it is possible for all the conditions to be satisfied, if it is impossible, that time return -1. So we have to find out the we have to minimize the maximum weight, right? Minimize the maximum weight. So what actually we can do? First of all, we will check that weight 1 is possible or not with weight 1. Then if it is possible to satisfy these three conditions, I will return 1. If it is not possible, I go to the next weight 2. In this way, actually I can actually increase the weight, and I can actually try to satisfy all those three conditions. So this is the linear search. So for this, the time will be big of n, right? So I can optimize this by using the binary search here, right? So binary search, how actually optimize this? So you already know about the binary search, that there are two pointer, L will be pointing to 0, R will be pointing to maximum value, and for I will get a mid value. So for each mid will represent the current maximum weight. This is allowed, and for this maximum allowed, I will check that I can satisfy those three conditions or not. If it is possible, then actually I will kept as answer, possible answer, and I will try to search to the minimum minimize the more. I will try to minimize more the weight. So right, so at that time I will shift the right pointer to the left mid -1, right? You all aware of that. So that's why I'm not discussing this binary search here. Now go to the threshold. How actually threshold? So what are the steps? So steps will be what? So steps will be first set the current maximum weight. So this, if it's from linear search, what will be the current weight? I will pass it in the helper function. And from the binary search, I will pass the mid as a mid value. Mid will represent the current maximum value. This is allowed. Okay, so this is, I will set this. Okay, now next will be what? Discard all the edges that those whose weight is actually greater than maximum weight, current maximum weight, or here actually the mid. I'm using binary search here. So I will discard this. Now we will get a one resultant graph that actually have less number of edges. Now I will do what? I will visit the graph. So by this visitation, what I will check? I will check that I can reach. Is there any? There should be. They mentioned in first condition that there should be at least one path that actually reachable to 0 from all other nodes. So I will visit the graph, the resultant graph. I will check that all nodes are reachable or not. Right? It will return true or false. Now next is I will check that second condition I have already setting here the maximum weight, right? So that's why second condition I have already set here. Third condition is that I have to check all nodes, the number of outgoing edges should be less than equal to threshold, correct? I will check that. Now I will check that this is actually matter or not in this problem. Okay, how? Now go to the check. So threshold value can be 1 between 1 to n minus 1, right? So it value should be less than at least 1, minimum is 1, right? Suppose this is a situation, this is our node 0 and this is some between intermediate nodes, and this is your target node. We want to check that maximum threshold number of, here is the threshold value is 3 now, maximum 3 outgoing edges can be present for this node, right? So how many actually outgoing edges are here? 4 in the input graph. Now suppose I have set the mid value, our maximum weight, allowed maximum weight is suppose 15. So which edges will be discarded? This edge will be discarded, this will be discarded, right? Now these two edges will be eliminated. Now I am doing the visitation on this resultant graph. So somehow I will check that this node is reachable. I can reach from 0 to this node somehow. Okay, I can reach. I have said this true. True means I am able to reach this node. Now threshold value is at least 1. Threshold value is at least 1. So if I am able to get at least one path to reach this target node, at least one path able to reach this target node, that means I like threshold value will be at least 1. So that's why it is sure that whatever the threshold value, I will be able to reach the target node in any way, right? Suppose this is both the path, there are two paths. This is one path and this is another path. Okay, I am able to reach this both this path. Now, but threshold value is suppose 1. So I have to choose only one outgoing edge. So suppose I can choose this also, any one of this. So I have actually extra option. Suppose our threshold value is, and suppose this is a situation where there are two paths. Now suppose only one path is possible and threshold value is still 3. Okay, but there is only one path to reach target node, this path, right? This path. So whatever threshold value is 3, so this is possible that this whatever the actually edge is, this may be present, may not be present. It is not actually problematic for our case, right? So this case actually, this edge will be actually mandatory to present in the actual graph, in the resultant graph, right? So that's why whatever the threshold value, it doesn't matter here. That's why I will not check that what that threshold value is like for each node there is actually threshold, maximum threshold number of outgoing edges or not, present or not, right? So that's why I can skip this threshold condition. Okay, so that's why I just remove this condition from here. Step 6. So from this, if I just visit the new graph, the resultant graph, if I able to reach all the all other nodes from 0, then I will return true. Else if it is not possible, then return false. And I have already explained why it is not matter. The threshold is not creating any problem here, because threshold is at least 1. And if I able to reach any one path, then it should be possible to handle that. I can actually remove all the edges, right? All the edges that actually greater than or equal to threshold, right? This is clear. The steps is clear. Now go to the actual code. So first of all, I have created the adjacent list. Where it will take two pair of vector of pair, and pair will take two things. One is the 2 and another is the weight, right? So I'm just iterating the edges vector, and just from why actually taking the reverse list here, reverse adjacent list, because I actually have u to v and w. Okay, now I want to check that from any other node 0 is possible to reachable or not, right? From 2 to, is there any path to reach 0 or not, right? So that's why we want to check. So if I reverse all the edges from 0 to this way, from downward, from 0 to this 0 to 1, 0 to 2, anyway 1 to 2. So what then if I start from visitation from 0, then I am able to reach 2. That means what? There should be one path to reach 0 from 2, right? Got the logic? So that's why I'm just what I'm storing, I am storing from v to u. In the index of v, I1, I am storing u and the weight. Got it? And answer is storing what? The whatever the maximum weight I have seen till now. So just taking what is the maximum value, answer, and the I2, current weight of the current edge. So if our helper function will check what? The current weight, the maximum weight actually I have seen till now. If it is possible to fulfill those three conditions, that then what will, then this is one possible answer. If it is not possible, then how actually we can minimize the weight, because this is the maximum weight I have seen. Suppose I have seen maximum weight 10 in the graph, in the input graph. So if I not possible with the weight 10, then how it is possible to weight 90, right? So that's why it is not possible with the maximum answers in the input graph, return -1, right? Got it? Now I will do the binary search. Binary search will take 2 pointer, L will be 0 and R will be 10 to the 6 plus 1. Okay. Now I am doing the while loop. This is the for binary search, and I will take the mid value. So for this mid will be the current maximum weight allowed. So if it is possible to this with current weight mid, then this is one possible answer. So I will take the minimum value answer, and I will shift the right pointer to the mid -1, right, to export the more minimum value. Else it is not possible with the current mid, so I'll go to the check the higher weight. So that's why I'll shift the left pointer to the mid +1. Got it? And at the end return answer. So how actually checking? We'll check. So this is the helper function. I am passing two things, or the maximum weight, current maximum weight we are allowing, and the n number of nodes and the current adjacent list. So there will be n nodes visitation. So I have to check that all node actually visitable or reachable or not. So that's why n nodes initially 0 indicates that not yet reachable. And q here actually I am using the BFS to visit the graph. You can also use DFS also here. So I am starting from 0. So q dot push 0 and visited 0 will be true as 1, set as 1. And count is equal to count initialize the count variable as 1, means it indicates that how many node actually I have actually visited. So while our queue is not empty, I will just pop the front node. So I will do what? I will just iterate the adjacent list of the current front node. I will check that the current edge, whatever the actually edge I actually have, it is actually considerable or not. How actually consider? I can consider if the current weight is less than equal to the maximum weight I am allowing. So I will get this from this input. So if it is less than equal to the maximum weight I am allowing, so that actually I can consider this current edge. So I will check that the current node is the target node from 2 U to V. So this node V is visited or not. If it's not yet visited, so that time it will be set to 0. So I will visit this. So I will just what will do? I will just increase the count, because this is a new node I am visiting. So that's why I increase the count and set the visited vector of this V as 1, because I am visiting this, set as 1, and push this into the queue. The V will be pushed into the queue. Got it? So if somehow if I visit all the n nodes, so that time return true. And at the end I will check that after while our queue is empty, I will check that am I able to visit all the n nodes. So it will be either true or false. Got it? So in this actually check that am I able to am I able to reach from node 0 to all other nodes or not. Got it? The problem statement and the intuition and how we actually using the binary search here, why actually and how actually the threshold is not influencing anything in this current problem. This is clear, and the steps also clear. So if you like the explanations, please like the video. If you any doubt, any confusion, any suggestion, you can comment on that. And please, if you not yet subscribed, please subscribe the channel. Thank you.